Hello again everyone, this is 2.3, Analyzing Graphs of Functions, and in this section we'll be talking about certain properties of graphs of functions. First let's recall what a graph of a function is, what we saw from the last chapter, or last section, 2.2. The graph of a function f of x is a plotting of the points x comma f of x, and the biggest thing to remember is that we always let y equals f of x. It's the y value of a point. So the visualization here is that if we have this curve that represents the graph of f, and we pick a particular x value, plot its point that corresponds to that x value, its y value will be f of x. All right. Next, we define 0. The 0 of a function f of x is an x value such that f of x is 0. So what the point would correspond to, remember the points are of this form, x comma f of x. So the x value will be x, and the y value will be f of x, which is 0 for all of these zeros. Okay, so a 0 is not the number 0, but it's a number that gives you 0 when you plug it into the function. Okay. Here if we have this curve of f, and these points here that I'm plotting, notice these points are just the x-intercepts, but they are of this form. They have y value 0. So we can actually say that f of x1 is equal to f of x2 is equal to f of x3 is equal to 0. So all of these values, f of these values are 0. So the numbers aren't 0. The numbers may be negative 1, 2, and 3 or something like that. But when you plug them into f, you get 0 as a result. Good. Also, what's nice to see here is that these are just x-intercepts. So if you wanted to visually find the zeros of a function, we can actually just graph the function and look for the x-intercepts. And the x values of those x-intercepts are the zeros. So we'll see some examples of that right now. Let's see what we have in store. Okay, so I've come up with these examples for finding zeros of a particular function f of x. So I'm labeling all of these functions as f of x, but it could be f of x, g of x, h of x, just whatever the name is. But yeah, they're f of x in this case. How do we find the zeros? Well, we're going to basically find the x-intercepts. We're going to set f of x equal to 0 and solve for x. So here, we want an x value such that 3x plus 18 is equal to 0. So let's see if we can do that. Subtract 18 to the other side, and then divide by 3. We get x is equal to negative 6. So this is a 0 of the function. Because when you plug negative 6 in, you get 0 as a result. The next one's going to be a little more challenging because we have to either factor and use the zero factor property, or we can use quadratic formula. I'm going to attempt to factor this. So let's see if we can use our factoring skills. So I know it would have to be 2x and x, and then these two numbers would have to multiply to 30. I'm going to take advantage of the AC method. So if we recall the AC method, we look for two numbers and multiply to the product of A and C, which is this times this, so it's negative 60, and add to negative 7, the middle number. And the two numbers that do that are, let's see, it's not easy to see ahead of time, but let's see if we can do this. So I got 60 is equal to 1 times 60, 2 times 30, 3 times 20, 4 times 15, 5 times 12, and all I'm doing is looking for the difference of these numbers because we want them to add to negative 7 and we want them to multiply to negative 60, so the signs must be different, and when numbers have signs that are different and you add them, you're really taking the difference. And notice here, the difference between 5 and 12 is 7. So the numbers that we're going to work with are 5 and 12. Now, 5 and 12 are not the numbers we're going to write here though, so remember how that goes. We draw a line through this, 5 and 12 like this, and then the number in front, the first term without the square, 2x. So we're going to get 2x over 5 and 2x over 12. We need to get the signs correct though. So it has to be negative 12 in order for them to combine to negative 7. So that's going to be 2x plus 5, and then after reducing this, we end up getting x over negative 6, so x minus 6. And we can check that this FOILs out correctly, but it does. You can check for yourself, but that's okay. Now I'm going to erase some of this and use the zero factor property. Okay, so remember for the zero factor property, you change the signs of the other numbers that are next to x and divide by any number in front of x. So here, changing the sign for 5 will give you negative 5, and then dividing by the number in front of x, 2. Here, changing the sign to negative 6 gives you positive 6. So these are the zeros, which, by the way, is negative 2.5 and 6. Okay, the next one's a little different as well. We want to find x values such that this fraction is 0. When is a fraction 0? Something we've actually seen a little bit before. I want to do a little more beyond finding the 0 here. I'm actually going to factor everything. Now notice factoring helped us here a lot. So maybe factoring this will help. Let's see. So if we factor the top can't be factored. The top is just x plus 3. The bottom, you can actually pull out a 2. You get x squared minus 3. You can actually factor this over irrational numbers. You can take it as a difference of squares. I know it sounds funny, but just kind of hear me out for a second. So this much is clear, I think, right off the bat. Now, remember, x squared minus a number squared is a difference of squares. It's x minus a number and x plus a number. So basically, we're going to square root each of these numbers, x squared and 3. When you square x squared, you get x. When you square root x squared, you get x. When you square root 3, you get square root of 3, which is just radical 3. Right? And the signs have to change. So one is negative and one is positive. This constitutes a difference of squares. If you FOIL it out, you'll exactly get this. So if you don't believe me, you can try it out. But it's kind of funny because we don't really need to do this. I'm doing this for a different purpose. But notice a fraction is 0 not when the bottom is 0. It's undefined when the bottom is 0. Remember that. A fraction is 0 when the top is 0. And you can see this by cross multiplying, because when you cross multiply, this whole expression that we just spent a little bit of time factoring, multiplied by 0 is just 0. So after cross multiplying, we're going to get the 0 equals to the numerator only. But an even better way of thinking of that is that a fraction is 0 only when the top is 0. Okay? Then subtracting 3 gives us that x is equal to negative 3. So that's our 0 there. Okay. So take a look at these answers here. I'm going to erase, but I'll keep the functions up. And then I'm going to look at graphs of the functions and then talk a little bit more about what happens when we take a look at the zeros. Also, I want to look at this. But we'll see that right now. So let me erase this and then we'll see that right now. Okay, so I've taken my time to graph each of these functions. And the first one is a line, the second one is a parabola, and the third one is some weird looking thing we haven't really seen before. We'll talk about that later. For right now, let's take a look at this line. Notice for all of these, they have x-intercepts, and the x-intercepts are exactly what we found for the zeros. So this 0 here is x equals negative 6, and it makes sense that the x-intercept is negative 6 itself. Of course, the y-intercept is 18. Y-intercepts are actually really easy to find because they're just f of 0. If you think about it, x is 0 for the y-intercept. So when you let x equals 0, you get 18. So it's pretty fair. It's a line because it's linear. So just find the 0 and the y-intercept, plug in 0, and connect those with a line. Good. This next one is quadratic. As it turns out, all quadratic functions have graphs that are parabolas. So this is a parabola, which is an opening up U shape that we've seen in class, I think, once. Also, so every linear function has a graph that's a line, and every quadratic function has a graph that's a parabola. Good. Now looking at the zeros, x equals negative 5 over 2 and x equals 6, we indeed get those as corresponding x-intercepts. Perfect. Now, of course, the y-intercept, if you plug in 0, it's negative 30. So I'm not really talking about too much of how I got the graph, but I'm just showing you that the zeros correspond to x-intercepts. And that's really the only big thing that's a big takeaway I want to say from this. There's something that's kind of interesting with this one, though. So it only has one x-intercept, negative 3. It has this weird shape, though. And remember that a graph of a function must pass the vertical line test. So for any vertical line, it does not cross the function more than once. Okay? it looks like there's possible overlap for a vertical line right here and right here. There's not, though. So what we get instead are what are referred to as asymptotes. So we get this vertical line that the graph doesn't intersect, actually. It's kind of interesting. I hope that comes out okay on the screen there, but it's this red dotted line I'm trying to draw. And here as well, let me try to make it a little more bold. Now if you're curious, the graphs or the equations for these lines are x equals negative radical 3 and x equals positive radical 3. And that shouldn't come as too much of a shock, because remember how I factored here and I said that it doesn't constitute for any, well, it doesn't have to do anything with the zeros, but it has to do kind of with something else. And this is what it has to do with. If you set the denominators equal to 0, you get where the function is undefined. So we can't plug in 3 or negative 3 because you get a 0 denominator, and that should correspond to something similar on the function. It's not in the domain of the function. So plugging it in will not result in an actual y value. So it's not an x value that's plotted as a point on the graph of the function itself. Okay, so I want to talk now about a little more about some other properties of functions. Right now we only really spoke about zeros, but I'm talking a little bit about domain here and y-intercepts as well. But next I want to talk about when a function goes up and goes down, and then certain properties from there. Okay, for these next properties of functions, I just want to discuss them visually. I'm not going to write down the actual definition using letters, and I'm not going to do it that way. If you want, you can actually take a look at the book. It's on page 191. Well, 191 and 1, they discuss this in more of a definition style. But I just want to go over the concept, because all we really need is the visual concept, I think, here. And the visual concept for increasing, decreasing, and constant are basically just when the function is either going up, down, or no vertical change at all. So here, from negative infinity to this point, to this x value, it seems, the function is decreasing. So from negative infinity to this value, let's call it a, we have a decreasing function. So what decreasing means is the y values get smaller and smaller. So as you go from left to right, it's going down. Let's call this x value b, and if we go from a to b, notice the function isn't going down, but it's going up as we go from left to right. So since it goes up as you go from left to right, from a to b, in contrast to from negative infinity to a, this is actually increasing. So the function here is increasing. But what happens from b to infinity? Well, from b to infinity, the function is remaining constant. There is no vertical change. So I can possibly talk about intervals of increase, decrease over here as well. But let me just write, let me write down here. As far as decreasing, increasing, and constant go, the intervals for which the function is decreasing, increasing, and constant are in interval notation: negative infinity to a to b, and b to infinity. Okay, but the visualization is that as you go from left to right, the function is either going down, going up, or not going up or down, just remaining constant. Good. Now for max and mins, it's a little more intuitive, I think, but a max is just the highest point in a location, and a min is the lowest point in a certain location. I say in a certain location because there are what are called relative or local max and mins, and then there are maximum, or I guess global max or mins. But let's really only talk about, for right now anyways, the ones we can see in the local sense. So here, this is a max, this is a max, and this is a min. Now the reason why I say local or relative is because it is a max only in this closed region. There are points that are above this max, like this one here. So where this max is an absolute max, and this max is only local because this is the largest of the maxes, but this is still a max in its own right. It's a little weird, but again, if it's just the highest point in this region, it is a max. If it's the lowest point in this region, it's a min. This, by the way, is local because there are smaller points out there. There are points with smaller y values, namely over here and over here. The graph seems to go below the y value of this min. Okay. The next thing I guess I want to say is that notice if we're passing through a maximum, that means our function went up and then went down, versus when we're passing by a minimum, our function went down and then is going up. So if I call these values a, b, so the x values that correspond to these points, a, b, and I guess c, then we see the following as far as intervals of increase, decrease. So where is it increasing and where is it decreasing? Well, it is clearly increasing from negative infinity to a. Then it is decreasing from, so it goes up from negative infinity to a, and then it's going down from a to b. So from a to b it's decreasing. But hold on, as soon as we go from b to c, it starts increasing again. So let me just say comma b to c. And then from c to infinity, it seems to be going back down. So just some example relating this idea of increase, decrease to what a max and min is. So the last thing I want to talk about now is something to do with symmetry that we saw before, but more of it from a definition standpoint as far as what it corresponds to as far as the function is concerned. Okay, so the particular definitions I want to talk about for these properties are what are called even and odd functions. So I say here that an even function is a function such that f of negative x is equal to itself, where a function is odd if f of negative x is equal to negative that function. And I give some examples here. Let's see if we can figure out which ones are which. By the way, these are called even and odd functions basically because that's what happens when you have powers that are either even or odd. So if you think of, like, just as a quick example, negative 2 to the third, well, 2 to the third is 8, negative 2 to the third is negative 2 times negative 2 times negative 2, so it's going to be negative because you have an odd amount of negatives, and then 2 times 2 times 2 is 2 to the third, which is 8. So negative 2 to the third is negative 2 to the third. So think of it like that. Whereas negative 2 to the fourth, let's say, an even power, you have an even amount of negatives, so it's positive, and this will be positive 2 to the fourth. So kind of try to see what happens here, so maybe ignoring the negative 8 part is a little easier to see. When you have odd powers, the negative pops out. When you have even powers, the negative just goes away. So now let's see if we can see what happens here. So for this one, we want to see if this is even or odd. We're going to replace x in the function with negative x. And let's see what happens. So anywhere I see an x, I'm going to write negative x instead. Just like that. And what do we get? Well, remember, negative to an odd power, the negative comes out. So this is negative x to the third like this without parentheses. Here we get a double negative, which is positive. And notice you can actually factor a negative out, and you get negative x cubed minus x. If you distribute this negative back in, you'll clearly get negative x cubed plus x. And notice this right here is just f of x, meaning the whole thing is actually equal to negative f of x. So in reality, this is actually an odd function. What makes it a little easier to see is that its terms are only odd powers. So that's some key insight I kind of gave you over there. Here, the powers are only even, and we have this constant term, but as it turns out, you can write this as 2 times x to the 0, 0 is even, and this is actually an even function. So let's see that by replacing x with negative x. So notice all I'm doing here is replacing all of the x's with parentheses first, and then filling each of those parentheses with negative x. Now what happens? Well, a negative to an even power, the negative goes away. So this is x to the 6th plus 3x squared plus 2, and that's back to f of x. In other words, this function is actually even. Okay, so why do we care about even and odd functions? Well, if you remember back from, I think it was 1.1, where we saw graphs of functions and certain properties of those, there's symmetry. And a graph of a function will have certain symmetry depending if the function is even or odd. So if the function is even, it has y-axis symmetry, where, so reflecting about the y-axis will give you the same image on the other side, which makes sense because if this is an x value, the y value it corresponds to is f of x, and if it's indeed even, then negative that value should correspond to the same y value. So that's the reason why they are actually that's the reason why even functions are actually y-axis symmetry, have y-axis symmetry. For odd functions, very similarly, if you pick an x value, you'll get, projecting to the function, you'll get a certain y value f of x. And if you pick negative that value, projecting to the function now, what you should get instead is negative that value you got otherwise. So really what this is what is called origin symmetry. Symmetry about the origin was 180 symmetry, so if you rotate it 180 degrees, you get the same image. So this is, let me just say, origin symmetry. Okay, and I believe that's the last thing I wanted to talk about. Yeah, that's the last thing I wanted to talk about as far as 2.3 is concerned. Really the biggest thing here was zeros, because we'll be using that, that vocabulary a lot later on. Max, mins, increasing, decreasing don't come up too often. Even and odd will come up later, way later on. But at least I introduced increasing, decreasing, and constant in this section, because like I said, we won't really be seeing it too much later on, but it comes up a lot in calculus. So just introducing an idea here, I think, is good, because it kind of plants the seed, so to speak, for what will flourish into something very beautiful in that topic of math. But as far as like immediate things, zeros is what we kind of need for this class a lot, and even and odd will come up later. But in any event, that was 2.3. Hope you enjoyed the video. It was a really fun stuff there. And we'll move on to 2.4. I'll see you in the next video. Thanks for watching.